Foster.
All right, so last time we introduced matrices as linear functions. So, or at least matrices can uh, we can describe linear functions on the plane as matrices. So uh, this is a this is a general linear function on the plane. Your input is x and y, or the output is some combination of x's and y's. So the way we constructed this was if we construct a matrix based on the coefficients of the variables in each coordinate, then this is a representative of the function as a matrix, which is really nice. So this is how we defined it. So in the matrix, your first row is going to represent the coefficients of the variables in the first coordinate. So the first row, A and B, will represent the coefficients in your first coordinate. So notice that A and B show up in the first coordinate. Your second row are going to be the coefficients of the variables in the second coordinate. So there's C, D in the second coordinate. And now the columns will be the coefficients of the variables. So A and C are the coefficients of X, that's your first variable, and B and D are the coefficients of Y of your second variable. So a way we can describe F is actually by a matrix, actual object, A, B, C, D, and that does the action of AX plus BY, comma, CX plus DY. Okay, so did anybody have any questions on just that formulation? It's just a way to describe a function as a matrix. So ones that we did in class last time. So maybe as we go through them, you tell me what they are. Can someone say what f of xy is going to be here? So the matrix represents the coefficients of the variables in each coordinate. So what do you think this first matrix is going to be? Just xy, yeah. Does anybody know what this function is called? Well, how about this? What does this function do? So you input a coordinate xy, and what's its output? What does it do? Yeah, it's an identity function, right? It doesn't do anything. It doesn't do anything. Right? So it takes in a point and outputs nothing, or it doesn't change anything, right? So that's a pretty boring function, but we'll see it's pretty handy. All right, what's this next one? You input something xy, and what's your output? What would your output be? Someone's mic's on. Yeah. Yes, negative xy. At the -1 in the first row, first variable means there's a -1x. There's 0 y's in the first coordinate, and then there's y. Does anyone remember what this function was? What's the function that takes an xy? Right, it's a y-axis reflection. Okay, how about this next one? Sorry, I didn't give myself much space. F of xy equals, which one was this? X negative y. Yes, and this is x-axis reflection. Okay, and how about this last one? It's negative x negative y. And that's origin reflection. Sorry, my computer's a little slow right now. And that's an origin reflection. Okay, what's this one here? F of x y equals what here? Yes, it's the reflection over x equals y, and it takes xy and flips it to yx. X equals y reflection. And then what's this one here? Negative yx. And do you remember which this one was? Yeah, 90-degree rotation. This is counterclockwise. All right, and I don't think I did this one last time, but this one is clockwise rotation. So it's y negative x. So this is 90-degree clockwise. Okay, so by the way, if you're curious about rotating in any, for any degrees, it's this formula here. And notice if you want to go clockwise, you do the negative of the angle. Remember, cosine is even, so negative of that would just be itself, but these signs flip. So that's why in the 90 degrees clockwise, the signs are different on this kind of off diagonal. So we might talk about this matrix a bit later, but if you're curious about how to rotate any degrees, it's this formula here. And notice if you plug in pi over 2, you get 0, negative 1, 1, 0. Okay. So now let's go from function to matrix now, just to get comfortable with this. Can someone tell me this matrix up here? So f of xy is equal to x minus y, comma, negative 2x plus y. What would the entries in the matrix? Yeah, 1, negative 1 is first row, and negative 2, 1, correct. Okay. Let's have this one here. f of xyz is equal to xy. So, strange one. So let me ask you this as we construct this. How many rows will there be? And how many columns will there be? Remember what the rows and columns represented in our definition. Other way around, it's going to be two columns, right? Remember, columns are, well, two rows, because the rows represented the coordinates in the output, and it's going to be 3 columns, because those represented the variables. So if there are 3 columns and 2 rows, what would our first row be? So remember, the first row is the coefficients of the variables in the first coordinate. Well, there's one x, I agree with that, but is there a y in the first coordinate? So 1, 0, 0. And what would your second row be? Correct, yeah. Rows equals number of output variables or coordinates, and columns is number of input coordinates. Yeah, you can think of it. 0, 1, 0. Why does it make sense that the z column is zeros? No z pops up, right? So of course there should be zeros. Correct. Okay, let's do this one. F of xy is equal to x, comma y, comma x plus y. So how many rows will there be? So remember, rows represented the coordinates. So 3 rows. And how many columns in this one? 2. Yeah, so it's kind of the opposite of the one we just did. Right? This one had 3 inputs and 2 outputs. This one has 2 inputs and 3 outputs. All right, so what's our first row? Remember, there are 2 variables here, so there's only 2 entries. 1, 0, correct? What's our second row? 0, 1, and our last row is 1. So you kind of get the idea of how we're constructing these. Okay. So here's some interesting last ones. How many rows do we have and how many columns do we have? Which is it, 1 row or 1 column? Yeah, 4 rows because there's 4 coordinates in the output, and 1 column because there's 1 coordinate in the input. Okay, so read out the column then. 1, 2, 3, 0. So that's it. And finally, how about this? We have f of xyz is equal to ax plus by plus cz. How many rows and how many columns? One row, right? There's only one thing here, and 3 columns. So, well, how does it read? ABC. So this might look familiar to some of you. Does anybody know? If you've seen it before, if you haven't, we'll talk about it later. Does this look familiar to you? Someone mentioned the word last time, but yeah, what is this? Yeah, this is dot product. So dot product is just some matrix multiplication. Y for the third one is 1 and y is 0. For the 1, 2, this one here. For the last row. Oh, the first row. Okay, yeah. So the first row, you look at the first coordinate. So there's only an x there. So that's why there's 1 x and 0 y's. And you do the same thing for the second and third coordinates. So the second row is the second coordinate. Third row is the third coordinate. Okay, so any questions on, so this was just redo the last one? Sure. So it's weird because this, right, there's only one thing here. So there's only one coordinate. So it takes three inputs, x, y, z, and it gives you one output, ax plus by plus cz. So there's one row because there's one output coordinate, and there's 3 columns because there's 3 variables in your input. So the answer is just ABC is the function, A comma B comma C. And then if you do it out as the function, this looks like something that some of you might know as dot product. Is that okay? So where did the A, B, C come from? It comes from the coefficients of x, y, z. So there's, is that okay? So these are the x coefficients, the y coefficients, and the z coefficients. Is that better?
So what would the answer be for that last one? Would we be using both of those parentheses things?
That is a yes, maybe, hopefully. Okay. Let me know if that's not clear. I'll move on, and I can come back. Okay, so now let's talk about composing functions. So we do composition even with higher, more variable functions, just the same as we do it with lower variable. But we have 2 things to think about. We have an x and a y to worry about. So here are 2 functions here, f and g. And let's think about composing f of g and g of f. So let's think about f of g first. So f of g of xy is just f of whatever g of xy is. Negative x plus 2y and 2x plus y. So you do this just the same as you would with, right, in one variable. What do you input? So here's f, and the x represents the first coordinate, and the y represents the second coordinate. So when you do the composition, the result is, well, you plug this in for x. So it's going to be negative x plus 2y. And then it's plus your second coordinate, 2x plus y. And then your second coordinate in your composition is whatever the first coordinate is, that's negative x plus 2y. And then you're subtracting whatever your second coordinate is, which is 2x plus y. So this is your x plus y. And this is your x minus y. So any questions on that construction? So this is how you do composition in more than one variable. So if you remember how it was done in one variable, like if you have, well, first of all, does anyone have any questions about that? I just want to make sure, can you hear me? Okay. Correct, yeah, you would distribute this negative. So the result, it would be negative x, oh, sorry, no, positive x, x plus 3y, comma, and this would be negative 3x, and then plus y. So that would be the composition. This is f of g. Oh, and the first one, y is a positive x because it's 2x and then minus x. So yeah, so let's do g of f and then you'll see the pattern. Okay, so we're plugging in f of xy into g. So can someone read out what it would look like? Well, or say what the first coordinate might be? So that's okay. I mean, read it. How? Yeah, let's read it all out first, and then we can simplify later. So it's negative of the first coordinate. For the first coordinate is x plus y in f. Okay, yes, we can do that first. So it's g of x plus y, x minus y. So that is, we plug x plus y into x, then plus 2, plug in x minus y, comma, then you plug in 2 times x minus x plus y, plus plug in the second coordinate, x minus 1. Everyone see that? So this is the x, in the first coordinate in f. This is the second coordinate in f. This is the first coordinate in f, and the second coordinate in f. Okay, so what is this? Negative x minus y plus 2x minus 2y. This is 2x plus 2y plus x minus y. So this is x minus 3y, and this is 3x plus y. Okay, anybody have questions on that? Anybody have no idea what's going on? So, okay, yeah, it's a bit different, right? We're plugging in 2 things instead of 1 thing. Normally, when we do composition, it's like whenever you see the x, you plug in the function, right? But there's actually 2 things going on here. There's a y and there's an x. So it's just a little bit extra work. So at any rate, you can see that the composition is different, right? If you do it in different directions. So the goal of what we want to accomplish here is, can we represent this composition of functions as with the matrix itself? So this is how we're going to find matrix multiplication, is what we're doing here in the composition, which is admittedly kind of complicated. It turns out to be a very, quote, simple calculation in the matrix, simpler than what we're doing here. So let's describe these as matrices and think about the results and how we got there. So what was our first one? It was x plus y, x minus y. So think of it like what we're going to define, it will make this a lot easier. So if it's complicated, don't worry too much, because the goal is that it's going to be less complicated in a moment. Okay, so someone read out the matrix for F. It's the matrix here. 1, 1, and then 1, -1. What's the matrix for G? -1, 2, 2, 1. Okay, so let's look at our f of G. So what we want to construct is a function or an operation that does this composition. So someone read out to me. So we found in the previous slide that f of G was equal to x plus 3y comma negative x 3x plus y. So what is the matrix of x plus 3y and then negative 3x plus y? What is that?
1, 3, and -3 and 1.
1, 3, -3, 1. Okay, so what we're going to do is, well, how can we get to this composition just by looking at the matrix? So let's just read out, let's do G of F, and then we'll construct the formula. And then we'll generalize it for any composition. Okay, so does everyone see kind of what the goal is? We're trying to define what this process is just by looking at the matrix rather than going through the whole composition like we did. We're going to develop a formula of how to get from here straight to here without going through that whole composition nonsense. Okay, so let us here. Okay, so let's think about the composition right here. So the result of this function on xy, let's maybe even put that in there. The result of this is negative x plus 2y and 2x plus y, right? That was our definition, right? So now we want to think about is what would this output be? Well, let's think of, so it's going to be two rows, one column. So we know that in our definition of the function, the matrix function, that the first row represents the coordinates in the first coordinate. So these are the coefficients of the variable in the first coordinate. So so know that so what we're doing here, so we're taking 1 times the stuff in the first coordinate and 1 times the stuff in the second coordinate. And then what this row signifies is the coefficients of the variables in the second row, or in the second coordinate. So this first one says 1 times the variable in the first coordinate, but this is a composition. And then minus 1 times the second coordinate. So if you think about it, in the composition, let's rewrite it like this. This entry is the x coefficient of x in the first coordinate of the composition. Now let's look at our result in our composition and say exactly, just read it out here. Well, there's 1 negative x here, and there's 1 2x here. So what this really is 1 times -1 from your first contribution here, and then plus 1 times 2. So that's here. I'm looking at these respectively. You can see kind of what we're doing. So we're doing the composition, kind of forgetting about x and y, and just looking at the coefficients. So we have our 1 1 in our first row in our first matrix, and we're looking at the coefficients of the first variable, and that our first variable comes from the first column in our in this case our second matrix. So that's the idea. So if you just look at what we have here, we're taking 1 times -1, and then we're adding it to 1 times 2. So we're bypassing the need for going through the composition and just looking at as some combination of the elements in the matrix. So now let's just kind of develop the formula pretty explicitly. So I'm going to do this again with random letters, and then we'll see what the formula is. So this is EX plus FY and gx plus hy. Oh, which one? Did I move the numbers around? Which one? Sorry, did I miswrite something? Oh, it did. Yeah, thank you. Is that better? Yeah, I miswrote that, sorry. So this result would be, let's write it down here. A ex plus fy. So I'm still doing the composition, but we're going to create the formula. Okay, so what is the formula? So this is the result of doing the composition like all out. And so we can develop what the matrix that does this function. So let's figure it out. So someone tell me what the first entry of the matrix will be. So remember, there's 2 rows and 2 columns. There's 2 variables, and there's 2 so there's 2 coordinates. That means there's 2 rows. So in the first entry, this would be the coefficients of x in coordinate 1. So here's coordinate 1. Someone read to me the coefficients of x. Yeah, we have AE. That's here. And we have BG. And it's plus, yeah. Okay, how about the coefficients of y in the first coordinate?
AF and BH.
AF, yep, because we're distributing, plus MBH because we're distributing. Okay, now we'll do the same thing for the second coordinate. What's the coefficients of x in the second coordinate?
CE and DG.
That's an E, by the way. So coefficients of x in the second coordinate. You got that one?
CDG.
CE, correct. So there's CE in this part. And DG is x. And then the y is, that's where CF is. We distribute. And
Then DH.
it's DH when you distribute. Okay, so everyone see that, how we construct the matrix there? So remember how we defined the function before was, or in the matrix, each entry represents the coefficients of some variable in that coordinate. So this was the result of doing it long ways, right, by as a function. And we fill in the blanks by looking at the coefficients of the respective variable. So now, wonderful, we don't have to do that ever again. And we have a nice formula for the product of 2 matrices. So this will represent composition of 2 functions. So what is the first entry here? Well, you look at the first row and the first column. So if this is A and this is B and this is AB, what is the result of what is AB11? Well, you take A11, you multiply it by B11, and you add A12 times B21. Everyone see that? So for those who know what dot product is, you might see this as dot product. So you're taking the dot product of the first row in the first matrix and the first column in the second matrix. So this is going to be the general formula. So AB12. So for AB12, which row do we look at in the first matrix? So this is this entry here. What row do we look at in the first matrix? The first row. Remember, this also comes from just this is the first coordinate, in terms of the function. And then what column do we look at? In the second, yeah. And then that's also because it's second variable. So we take A11 times B12 plus A12 times B22. Okay, and so we're almost there. So for AB21, what row do we look at in the first matrix? So this is this one. Yep, second row. And what column of the second matrix? First. Okay, so we have a 2-1 B11 plus a 2-2 B21. So I'll just do the last one. It's a 2-1 B12 plus. Okay, you're lost. Does this formula make sense up here? I'm just relating now the formula up here down to the indices that we've talked about before. What are we doing with AB? So this is the product, is what we're defining as the product of these two matrices. So I'm just, is that okay? I'm just showing you what, so this entry here is 1-1 of the product, right? And I was just putting it back into that other notation that we talked about with the indices, because we're going to use that notation. So I just want to bring it back to that notation. So remember, this represents the row and the column. So AB11 is the first row, first column here. And where are these entries? So AEBG, AEBG. So that is, this entry A is A11. A12 is here. This is first row, second column. And that's here. B21, that's here, second row, first column. Yeah, so let's just remind ourselves what that notation means. Or we can even just use. This means it's the entry in first row, second column. Yeah, it is a little easy for us. There's a lot of indices that we may not be comfortable with just yet, but we'll use them a bunch where it'll become easier. But please do stop me if it gets a little overwhelming, because we're going to use these indices a lot more. Just want to make sure. So we want to make sure we, kind of understand that now rather than just keep getting lost. With these indices, yes, the functions is later in the textbook, but I wanted to kind of go through that route so that when we get to this is pretty much the definition of matrix multiplication, and then it just seems to come out of nowhere, but with the idea of the function composition, it kind of has a purpose. But we're developing the what matrix multiplication is in terms of functions. But this formula we're developing here, that will be in the textbook. All right, so how about someone read for me the last one? So AB22 is this entry here. So can someone read CF plus DH in terms of the indices? So CF plus DH, what is that in terms of the index or of index notation? So what is C? How do you read C in A?
A21.
And then what's the index? What's the subscript?
21.
21. Yeah, that's the second row, first column. And so we multiply C times F. So what is F in the index notation?
B12.
B12. Professor, can you hear us?
Correct. It's B12.
Can you hear us, Professor?
Row, second column. So this is C, and this.
I think he has
F.
us muted or something.
Oh, are you trying to speak? Did I accidentally mute? Can you try to unmute? Maybe you're muted.
Can you hear us now?
Can you hear us?
Are you speaking now? I
Yes.
see someone's mic on, but I can't hear for some reason. Yeah, I can't hear. I don't know why. I have my volume on. I'm sorry. Audio source. Shoot, I don't know. Speaker, where is that? Command. I guess I'll have to figure this out later. I don't know what happened. Okay, yeah, if you could just type it out in the meantime. I'll try to figure it out by next class. Or maybe like do a test in the beginning of class. Yeah, sorry about that. All right. Yeah, so could you so So if you had questions, I'll give you some time to type that out. Yeah, so it's A22, B22. A22 is D, and B22 is H. Okay. Okay, so we'll do a lot of examples of these, so this formula will become more ingrained. So right now, I agree, it might feel overwhelming, but we're just starting. Yeah, there is absolutely a pattern. So I just want to take a brief little, so let's do some examples first. Why don't we just do that? And then we'll develop the general formula. Yeah, exactly. This is totally new things and a lot of new things to work with. Okay, so in the first entry of the matrix, we look at the first row, first column. So we take the first entry times the first entry in the column. So it's 1 times 5, and then plus second times second, 2 times 7. So this is the first entry in our product. Okay, so now let's do this second entry. So it's the first row and second column. Corresponds to the first row, second column in the product. So it's 1 times 6 plus 2 times 8. So now you tell me, in the second row, first column, what row and column are we looking at in the factors? Yes, we're looking at the second row, first column. So 3 times 5 plus 4 times 7. Good. And then how about the last entry here? Yes, we look at the second row, second column. So that is 3 times 6 plus 4 times 8. Good. So what is that? 5 plus 14, 19. 6 plus 16, 22. 15 plus 36 is a number. So whatever those are. Okay. So let's do some other ones. Let's see. So in our, let's do different dimension matrices. So for example, let's think about go back briefly to composition. And we'll use this to explain when can you multiply 2 matrices and when can't you multiply 2 matrices. Okay, so does anybody know, when thinking about the domain of a composition, what do you have to worry about? Like if you have domain of, let's do a classic one. Let's do like, oh, that's, okay, so if you have f of x is equal to 1 over x and g of x is equal to 1 over x, can someone say what f of g is? yes, that's the general idea. So the domain, well, not the domain of F, but the domain of F of G must include the domain of G, right? So F of G here is 1 over X, which is equal to X. So 1 like the identity. So you're plugging in 1 over X into X. But yeah, so the domain you would look at the domain of this, of F of G of X, and you would also look at the domain of the input. So what is the domain of F of G of X equal to X? In this case here? So what number doesn't work when you plug in? Just zero, right? So the domain is X can't equal 0. Okay, so the idea here, and now it would be, well, in this case, negative infinity to 0 and 0 to infinity. So you have to include that negative stuff too. So the idea is that when we think about matrix multiplication, this is composition of functions, we want to think about, well, the domain of the composition is the product. So when we think about the product, we have to consider the domain of each individual function. So for example, if we have, let's say we have a function f of x, y, and let's say this outputs something in 3 variables, x, y, z. So the domain is anything in 2 variable space. And the output space is 3 variable space. So think about when we do composition, if there is some G, what do you think the input space needs to be? If I want to do G of F, what type of, what input would I need to input G? If F outputs something in 3 coordinates, what must input for G? So the idea is that the output of F needs to make sense for the input of G. So relating that, in this case, the output of G is 1 over X. That needs to make sense when you plug it into F. So that's why you need to consider G. So the output of F needs to make sense with the input of G. So if F outputs 3 variables or 3 coordinates, what must the input of G be? If I want to make sense of a composition. It must have 3 inputs. Sorry, yeah, let me just repeat it. So let's say F inputs things and then outputs something. Now, if I want to apply a different function G as a composition, this output of F becomes the input of G. Correct? Does that make sense? That's what a composition is. So whatever F outputs, G then inputs. So the question is, and when is a composition valid? It's this intermediary step here. When is a composition valid? When is it valid if the output of F is valid for the input of G, or as input of G? Does that make sense? So suppose F outputs something that G cannot input, then you can't make a composition, right? Think of it like if F outputs colors and G only inputs fruits, you can't do the composition because G has nothing to input. So or the output does not align with the input. Or sure, okay, that would be the only thing that G could input. Right, so does that make sense? So when thinking of a composition, we need to think about the output of G. So this is the output of G, and how that aligns with the input of F. So you write an example that's invalid. Sure. So here's an example. Let's say F of x, y is equal to x, y, x plus y. And you have G of x, y is equal to y, x, x plus y. Can you compose those two things? Composable? So why is it not composable? So let's actually just try writing it out. So what would be F of G of x, y? F of y, x, x plus y. Why can't I do that? And it's not anything to do with these, but look at what is F of x, y input? Yeah, there's too many inputs, right? F only inputs two things, but G outputs three things. Yeah. So what needs to match is the coordinate space, if you want to think of as functions, the coordinate output needs to match with the variable input. So the number here would need to match the number here for the composition to work. So let's do one that would work. It also would not work for G of F, right? Because it's the same problem. Okay. So if F of xy is equal to x, y, x plus y, and G of xyz is equal to x plus y, y plus z. Yes, the output space needs to match the input space. So when we think about matrices, think to yourself, how do you say that in matrix terms? So does this what I have here, is this composable? So let's check it. So f of g would be f of x, y, x plus y. So this is okay. You take x plus y, and whatever is your y is y plus x plus y. So that's okay. How g of f. So it's g of x, y, x plus y. So your first coordinate is x plus y, and then y plus z. Oh, sorry, x plus y. So x plus y plus y plus z. So that's okay. So yes, the output of the first thing in your composition, by first I mean closest. Oh, yeah, so remember what these mean. So G is x plus y, y plus z. So this means your first coordinate, which is your x, plus your second coordinate, which is your y. That's why you get x plus y. And then y plus z is your second coordinate, which is y, plus your third coordinate, which is x plus y. Oh, sorry. So this should be sorry, yeah, y plus z. F of g, yeah. So here's g, it's x, y, x plus y. So we look at f, and your first coordinate is whatever oh, I'm sorry. I put f here. That's f of f. That's correct, right? Sorry, yeah, I did f of f. Oh, something went wrong there. So what is f? And the first coordinate is whatever your first coordinate is. So it's x plus y. Your second coordinate is whatever is in your second coordinate, which is y plus z. Sorry about that. Your third coordinate is I'm sorry. Your third coordinate, which is here, is whatever is in your first plus your second. So this is x plus y plus z. Sorry, and it's not. I'm sorry, I'm getting bogged down by the specifics, but the idea is that the output space of your input needs to equal the input space of the second one. So in that language, let's think about matrix multiplication. So let's do does this make sense? What is the outputs in what is the input space, first of all, of this first matrix? No, sorry, let's do of this one. What is this input? So what is this as a function? F of what? Yeah, f of x, and then it's x 2x. So it outputs two things, two coordinates. Now, what does this do? So how many variables are there? Inputs 3 and outputs 2. So is this composable? Think about it. This is your output, and this is your input of the second one, right? So these do not match. So what, in thinking about rows and columns, what needs to match? So, okay, so first of all, the 2 here, what is that? 2 of what? The number of rows in the second matrix needs to match the number of columns in the first matrix. Okay, so sorry, we're out of time. We'll do more of this tomorrow. So this was really just introduction to even get to talk about matrix multiplication. So, next time we're gonna do a lot more examples of stuff, and we'll come up with kind of the general formula. But we'll need to go, I'm not sure, I know some of you may have familiarity with the sigma sum notation. So I'll do a brief little, refresher or explanation of what that is. And then we'll develop the formula. But we're going to spend a lot of time on matrix multiplication. So if today was confusing, don't worry too much. But I'll stop the recording here, but I can still stick around for questions.